play it for a
All right. On Thursday, we talked about something called the Descartes rule of signs, which your assignment is going to ask you to understand it, to make an argument about it, okay? And it is useful, but in general, because we have a little bit better technology than Descartes did when he was coming up with this stuff and recognizing this stuff, we're going to kind of, for the most part, when our overall task is to factor a polynomial, we're going to kind of maybe ignore his rule of signs. It does help maybe beneficially in regards to doing this stuff by hand, and even with your calculator, it might provide some insight with your calculator, but in general, a lot of times, the only use of this theorem that we have, or that we see, is in homework when they ask you, just verify a relationship for us. So what we'll do here, Rene Descartes, his rule of signs was, the idea is if we see in P of x the fact that we have this many changes or variations in sign, and that tells you this is how many positive zeros you're going to have, positive real zeros, or that remove a whole even number. Okay, so you start subtracting basically multiples of 2 from that until you get to 0 or a negative number. Okay, so let's say that P of x is to the 5th degree, and let's say I have 4 sign changes. Then that tells me in this P of x I could have 4 positive zeros, or subtract 2 from that, I could have 2 positive zeros, or subtract 2 from that, I could have 0 positive zeros. Does that make sense? And then the same thing happens with negative zeros, but to figure out negative zeros, we have to find P of the negative x, or P of the opposite of x. Okay? And if you remember what multiplying the x by, okay, multiplying the x by a negative in a function, transformations, what does that do? What does multiplying, if I take a function, let's just say I have, y is equal to f of x. If I multiply by a negative out front, that flips it over what? The x-axis. What's that negative right there do? Y-axis. Okay? So if you're kind of visualizing what's happening here, is that if we've got P of x, okay, and it looks something like that. Now I don't know exactly what the function might look like in polynomial form, but I do know that I've got 2 real zeros here, right? Okay. Well, if I multiply by a negative x, what that's going to do is it's going to take that graph and it's going to flip it over the y-axis, right? Look like that. And now you're going to have 2 negative zeros over here, correct? Does that kind of make sense? Okay. So the test, I guess, that's happening in kind of the background here is describing that behavior. Okay. So how many times do you have a negative 0 in P of opposite of x? And that's going to help us determine how many negative zeros you could potentially have for your original polynomial. And it all has to deal with transformations and that understanding. But it says if you can find P of the opposite of x, okay, you find the sign changes that occur in that, you're either equal to that or remove 2 a multiple set of times. And that's how many negative zeros you get. So if I have 5 sign changes in P of negative x, 5 sign changes in P of negative x, then I could have either 5 negative zeros, or I might have remove 2 from that, you might have 3. Remove 2 from that, you might have 1. Remove 2 from that, you get negative 1, right? So you can't have negative 1 zeros. That doesn't make sense. So 5, 3, or 1 would be my options for the number of negative zeros you can have. Okay. In your homework this evening, they're going to ask you that kind of stuff. They're going to give you a polynomial and say, hey, write down the number of possible positive zeros you could have for this function. Write down the number of positive negative zeros you got for that function. Okay. In having that insight, might make things in the long run a little bit easier as we start trying to kind of dwindle our P over Q list for factoring these polynomials. Okay? Remember, our P over Q can be very large, right? The bigger our constant value is, the more factors it has, and then the more factors that our leading constant has, or leading coefficient has, that list becomes very large very quick. And if I've got a thing, let's just say 24 is my number over here. Let's say my A term over here is 24. And let's say my A sub n number, which is the leading coefficient, let's say that was 4. That would give me, I think, 48 P over Q's to check. We don't want to have to do synthetic division 48 times, right? And even with that list of P over Q, we might get to the point where maybe that last one that I write down, maybe 24 over 4 is the last number that I check. So I check 47 P over Q's before I find the 1, 0 that I need for my function. Does that make sense? That would be a really long, tedious, pain in the butt type thing. And that's what these guys a long time ago were kind of figuring out, that yes, this is useful, it's going to be being able to factor something's nice, but it's really time consuming. Can we find some concepts, some ideas that'll alleviate some of the work? Okay, and these theorems are that. Okay, so it tells me, if I've got, for instance, let's say that we use his rule of signs, and we find out that we have one variation in sign. Okay, for P of x. So let's actually go down to, I don't know if I've got a good one here. Oh, this is it. Okay. This is the only time that we have a variation in sign right there, correct? Everything else is positive, positive. 4 to 3 is positive, positive. But positive 3 to negative 1 is a sign change. Okay? And then negative 1 to negative 3 is no sign change. So that's the only place that a sign change is occurring. So that tells me that we have the possibility of having one positive real 0, right? So then when I find a positive real 0, when I start going through and choosing P over Q's and I find a 0, and it's a positive number that I use to find that 0, do I have the ability now to basically cancel all the other P over Q's that have positives in front of them? Yeah? Okay. So that cuts your list in half at some point. Okay? Which is really nice. Okay? And it also tells me that down here, if I look at P of negative x, okay, I've got 3 sign changes, right? Okay? So 3 sign changes tells me in P of negative x, that tells me I can have 3 negative zeros. Okay? I could have 1 negative 0, correct? Now think about this. Okay? Just logically, if this is 6th degree, and let's just say that it's going to factor down to all rational zeros, and I just realized using René's, I keep calling him Rene, Descartes' rule of signs, his first name was Rene. If I use his rule of signs, it's saying that you have 1 positive 0 over here, and you could have, at most, 3 negative ones, right? Well, if this thing's a 6th degree polynomial, and we know that it's going to factor down to 6 rational zeros, and his rule of signs tells me right now that I only see 4 up there, right? What's that tell me about one or maybe a couple of those zeros? They might have what? They might have a multiplicity, okay? Is that going to make sense to everyone? All right, so that tells you, and when you find, and just a reminder, when you find a 0 going through synthetic division, try it again. Okay, if maybe we go through this procedure and it's a 6th degree polynomial, and we find out that we have 3 positive zeros and 3 negative zeros, then maybe it eliminates the use of multiplicity. Okay, what happens here in a little bit, guys? We're going to use our calculators to kind of circumvent this rule, okay? Not have to really apply it too much. But what your calculator doesn't do for you, your calculator doesn't tell you that you have multiplicity. So you still have to be able to do some of the synthetic division stuff and have an understanding of the concepts that we're talking about, so that you can recognize all the factors that come from your graph. So Descartes' rule of signs is useful. But together with this theorem, it's much more beneficial. Okay, this is called the upper and lower bound theorem. Whenever you talk about bounds, Okay, it's the root word for boundary, right? Okay, so meaning that you're not going to go beyond these values. Okay, so if I got a lower bound, that means that's the minimum value that you can look at, or that you're going to have to look at. If you have an upper bound, that's the largest number you can look at or have to look at. Okay, so here it says we say that A is a lower bound and B is an upper bound for zeros of the polynomial if every real zero C satisfies that inequality. Okay, where C is between A, which is your lower bound, and B, which is your upper bound. Okay. But then here's what this theorem says. Okay, and this becomes useful, and you see this pattern exists a lot of times when we actually do the synthetic division, we get a zero. But it says if we divide P of X by some factor, where your B value is positive. Okay, so we've got some polynomial, and the number that we're putting in here is positive. Okay, it says when you divide using synthetic division, and your last row has no negative entry. So maybe my last row, and then I'm talking about my quotient row here, maybe it looks like this. Something like that. Don't even care, but just no negative numbers, right? Now 0 is non-negative, right? So basically in this whole theorem, it becomes a real important part too. You can treat 0 as anything you want, whether it be positive or it be negative. Does that make sense? However you need to use it. So right now I'm going to say 0 is a positive number. Okay? But if this is the case, what this tells me is whatever this number was, maybe this number was 3. That tells me now that there are no values, there are no zeros that are beyond 3. Okay? There are no real zeros, rational zeros, that occur to the right of 3 because of all of these values here being positive. Does that make sense? Okay? So that's nice because what if my list of P over Q's looked like something like this? I have some really weird A and A sub n values, but what if my list of P over Q's is this? I just found out that 3, even if 3 can be one of my P over Q values, but doesn't have to be. I can divide by anything I want to. Okay? But I just found that 3 is an upper bound. So that tells me positive 6 doesn't work, positive 7 doesn't work, positive 12 doesn't work. I can cancel those out right away. Does that make sense? Okay? And I just dwindled my list a little bit. Okay? What the second part of the theorem says is if you divide by a negative number, let's say I put negative 2 in here, okay? And it says using synthetic division, if your last row alternates positive to negative, okay, then A is what we call a lower bound. Now it doesn't say that real well here. It says using synthetic division, and if the row that contains the quotient, so again this row here, okay, has entries that are alternately non-positive and non-negative. Non-positive and non-negative. It's kind of a weird way of saying it, but what it's saying there is that as long as your row alternates plus or minus, you're going to have a lower bound. But what happens when you have a 0 in there? What that non-positive and non-negative phrase is saying is that you can take 0 and treat it however you want to. Okay? So let's say that I have plus 2, negative 3, negative 5, plus 7. Okay? If I look at this, positive to negative, and then if this is going to alternate, I would want this one to be what? Positive. So I'm going to treat 0 as positive. Okay? So positive, negative, positive, negative, positive. It alternated, right? Okay? What if I did this? What if my values were negative, positive, that? Negative, positive, I'd want that 0 to be negative. Okay? So the non-negative, non-positive thing is saying take your 0 and treat it however you want to treat it. Okay? Does it need to be a negative here or does it need to be a positive here? And that would be useful. If this occurs, that tells you that this negative 2 was a lower bound, okay? And nothing to the left of negative 2 on the x-axis is going to be a rational 0. So what's that do? Crosses those out, and now my P over Q, obviously negative 2 is not a 0 either, but my negative 2 has now created my P over Q list to be much smaller. Does that make sense to everyone? Okay. Now, here's the thing. How do we know which of these to choose? How do I know at the beginning to start with, I always start with the first one because I just don't know. How do I know to choose -2? How do I know? And I don't have the answer to that, okay? Some people just randomly start in the middle of their P over Q list and they start using division then, okay? And then they maybe move to the right or they move to the left, okay? Or they just kind of hop around using P over Q values, okay? Maybe they look at their coefficients and say, okay, all my coefficients here are even. Maybe a 1/2 would be a nice P over Q value to start with, okay? There's no rule that says you have to start with the first P over Q that you come up with. Does that make sense? You can choose anyone out of that list to start with. So that's something to think about, something to maybe use as we're going through these questions. Now, that being said, we're going to do something with our calculator that kind of gets the ball rolling in regards to how to factor these things. Okay. But what I want you to understand is that your calculator, and really any technology, has some coding in the background, right? And we want that coding. If you've ever done any computer programming or anything like that, you do not want a real cumbersome program, okay? You don't want something that's in the background doing a lot of calculations. You want to minimize those calculations, because the more calculations that I have operating in the background, the more memory that I have to use, right? The longer that program starts to take to work, okay? And ultimately, as a programmer and as a company writing software, that's more money. The more complicated my coding is, the more expensive it's going to be, because it's computer time, it's RAM, it's accessible memory, that kind of stuff. So we're wasting money. Does that make sense? So we want our programmers to write these things, write these codes to be efficient, to happen real fast. Okay. Just kind of give you an example. I'm doing my homework for Finley over the weekend, and it's a very powerful computer program, and every time I do I can't get through my homework right now, because every time I do a specific calculation, it freezes my entire computer. My computer will not, it just goes like it sounds like a car backing up, or like a pickup truck, or like a U-Haul backing up all the time. And I have no idea what's going on. I just can't do homework anymore. But we want our programs to be efficient and to happen fast, right? Some of you might be working with your TI-83s or 84s, and you might do a calculation, especially when there's a computer solving system on your calculator. You might hit enter, and it might be thinking for a while before it spits back an answer, okay? Because it's doing a lot of calculations in the background. That all being said, these two theorems are used or could be used in the coding for your calculator, so that they can efficiently determine zeros, efficiently find you the picture of your polynomial. Does that kind of make sense to everyone? Okay. Now, I don't know if that's true in the TI-83 or 84. It might be true in the TI-89, okay, because they're a lot more powerful. They have a computer solving system in them. So on like a TI-83 or 84, I type in a function, or sorry, TI-89, I can type in a function and hit factor, and it will factor it every single time. Okay, so it'll do all the work that we're looking for right now. So in its coding, it probably has these two ideas wrapped up into it. Okay, which is really nice. All right, so in your homework, they're going to ask you, they're going to say, okay, here's a polynomial. Take these two numbers and prove through synthetic division that -3 and +2 are upper and lower bounds. So all they do here is they take 2 and they run it through synthetic division, and they find that they have all non-negative entries down here in the quotient line. And if all those things are positive or non-negative, could have a 0 in there if we wanted, that tells us this positive number was an upper bound. Okay. Then they try -3. They recognize when we do that division, we get alternating signs. So because of alternating signs, it tells us that -3 was a lower bound. So then I know that I don't have to choose any values that are to the left of -3 to be a 0, or to the right of 2 to be a 0. Okay? All my zeros are going to occur between those two numbers. What's nice for us calculator-wise, even though we're probably not going to specifically use this theorem very often, other than direct homework questions when they say prove or show through synthetic division that these are the boundaries. When we type something into our calculator, we don't necessarily know initially what that function is going to look like, so we might not know what window to choose. Okay? We don't know how well to zoom in, how far to zoom in, or how far to zoom out, that kind of stuff. So this might be maybe a preliminary thing to help you determine what that window is. Okay? And to verify, to confirm, guarantee, I guess, maybe a better word, that in your window, in your view screen that you currently have, you know that all your zeros are showing up. Okay? What I always fear with when I'm graphing something is that, let's say that I graph that polynomial, okay, and I see that I got 3 zeros there, okay, but I kind of fear, what if there's one, what if I zoom out all the way over here, and there's another one like over here on the left-hand side of the x-axis, beyond like -10 over here. Is that going to make sense? Okay. The upper and lower bound theorems will guarantee me that there is nothing over there, okay, after we do a little synthetic division. Does that make sense, everyone? All right. So I want to show you a couple examples here of how all of these things kind of relate. And like I said, will we use these specifically? We might, okay? But I think also what's interesting is that we should be able to kind of go through the tasks that we're going to be asked here in a moment. And as we do the synthetic division, we should be able to recognize these relations. We should be able to realize that, hey, if I choose -2 right here, because that's going to be the 0 right there. If I choose -2 for this polynomial, and I look at the remainder of the quotient line, okay, it's going to be all, it's going to be alternating signs. And what that tells me then is that -2 was a lower bound, and that there guarantees then that there really isn't one of those zeros that is maybe lingering over here on the window that I can't see, okay, or outside the window. Does that make sense, everyone? Okay. So let's go ahead and let's write a function down. Let me give you a polynomial here, and actually let's just do this. Let's go that polynomial right there. As we're doing this stuff, okay, we are trying to factor, and my hopes are that you guys realize that, let's say I'm on the ACT or a college entrance exam, or I'm in a calculus class and I need to do this. My hopes are that you don't do the P over Q stuff and be very slow and methodical about the work involved in that, because there are better ways with using our technology to get our solution, okay? But our calculator, the way it's programmed, the way we use it, we still need to understand everything that P over Q is saying and what it does for us, even if we're not going to use it kind of word by word, letter by letter. Does that kind of make sense? Okay. Because this calculator, the technology that we have, allows us to circumvent a lot of work, but that doesn't mean we can circumvent the understanding of that work. Okay. If I have P of x is equal to 2x to the 5th plus x to the 4th minus 32x minus 16. Okay? We want to find all our values P over Q. Okay? So in your homework, you're going to see a variety of different styles of questions. First one is going to say, just list all the possible rational zeros. Well, that means find from that all your P values. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, right? And then from this one, find all your Q values, plus or minus 1, plus or minus 2. And then to answer the question, they're wanting this, P over Q, plus or minus 1 over 1, plus or minus 1 over 2. So I take that one and I put it over both those. Then I do the same thing for the second P. So plus or minus 2 over 1, and then plus or minus 2 over 2. Well, plus or minus 2 over 2 is what? 1, which we already had, right? So I'm not going to write it twice. Okay. Then we'll go to the next P value, so plus or minus 4. Put that over 1, and then plus or minus 4 over 2. So plus or minus 4 over 2 gives me the 2 that I already had, right? So every once in a while, you might have some redundancy. So I'm only going to write them once. Then I got plus or minus 8 over 1. And then plus or minus 8 over 2, which again is that 4. Okay? And then I get to the last one, plus or minus 16 over 1, and plus or minus 16 over 2. 16 over 2 gives me the 80. All right? I don't know how WebAssign kind of gauges your answers. If you have, like in this situation, if you had a plus or minus 1 and plus or minus 2 over 2 in your solution box, I don't know if it would count that right or wrong. Okay, I think the safest thing is to eliminate repeat values. Okay, so those are possible values of P over Q. The next thing will be, okay, how do I determine some zeros? Okay, and they might ask a question like, take, I don't know, like -4. Okay. And say, show that -4 is maybe a lower bound, okay? So as we're choosing our values of P over Q, when we do this thing here, when we do our synthetic division, okay? I got 2, I got 1, 0, 0, -32, and -16, right? You gotta have those placeholders. When we do the synthetic division, I don't know which values to choose, which P over Q to put in that box first. Our calculator is going to help us decide that here in a little bit, but let's just say I chose to look at -4. So I put -4 in here. And I'm going to do my synthetic division. I bring down my 2, multiply, I get -8, so it gives me -7. Multiply gives me 28, I do positive 28. Multiply gives me, it's 28 times 4, 112. -112, so -112. Now that's going to be 448, right? 448. That's going to give me let's just think about this. That's going to be a positive number, right? And you could do the math if you want. You add that together and get what, 16? That's fine, you do that. But then 416, a big positive number times a negative is going to give me a negative, right? What's a negative plus a negative? Negative plus a negative. Be negative again, right? A bigger negative number. What do these numbers do? Positive, negative, positive, negative, positive, negative. Alternated, right? And if this is a negative number and your quotient line alternates, okay, the lower and upper bound theorem says that -4 needs to be a lower bound. So what's that do for us? If -4 is a lower bound, 4 is not a 0, right? Those two numbers are not going to add up to give me 0. So it says -4 is not a 0, so you can cancel that out. It's not a root. But it also tells you -8 and -16 are not roots as well. And you can cancel them out. And it just made your list a little bit thinner, right? Okay. Does that make sense to everyone? Can we do that? Okay. Now, here's what we're really going to do. We're going to type this thing into Y1. And I consider this cheating, but I don't know that it is because your book actually asks you to do this. They ask you, can you find, from looking at a graph, can you start recognizing some zeros? Now, I know, just because of what we just did with that synthetic division, -4 was a lower bound, right? I'm not going to have a 0 to the left of -4. So maybe what I could do with my window is instead of looking at -10, I know I'm not going to have to look at anything beyond -4. So maybe I change my window a little bit. All right, it might make my graph a little bit easier to look at. Okay, zoomed in a little bit, right? Okay, and I look at my graph, and maybe I look at this and say, okay, this looks like 1, 2, and then 3, right? I'm not sure, I'm not confident that my graph doesn't shoot up to, you know, positive infinity over here, but then do it over here. I'm not sure that this graph might, come on. It's there somewhere. I'm not sure whether it might come back down over here, right? On the other side, okay, where I don't have the window enlarged to. So let's say that, you know, this value here is 3, okay? Well, let's try synthetic division. 2, 1, 0, 0, negative 32, negative 16. If I put 3, and let's see what happens. You get 2, 6, 7, 21, 21, 63, 63. Now, 63 times 3 is going to be a large positive number, right? Okay? It's going to be bigger than negative 32, so this is going to be positive. And then a positive times a large positive, just kind of think, I'm not even going to do the math here, but I know that this is going to be a 60, what's 63 times 3? 9, 189. Add those together, okay? You need a pretty large positive number, at least 100, right? 3 times 100 is 300. Is negative 16 plus at least 300 a positive number? So what happened here? All positive entries in that quotient row, right? So all positive entries tells me that 3 is in fact an upper bound. So I know now that maybe if I want to, I can go to my window. I hate this thing. Go to my window, and I can change my x maximum to 3. Go back to graph. Now, at least in regards to the x-axis, that's a much better looking graph, right? Okay. And I can be guaranteed now, because of the upper and lower bound theorems, that I'm not going to have any zeros that are hiding from me outside my viewing window. Okay. And that's kind of what I was talking about earlier in the class is, are we going to use these theorems directly? Probably not. But when I go through synthetic division and I get a result, what is that result telling me? Okay. Can I guarantee that, you know, there are no additional zeros occurring elsewhere? And in this case, we can. So, positive 3 is an upper bound, so that tells me those are gone. And these then are my only possible things to look at for zeros right now, right? And we still haven't talked about lower bounds. All right, yes, sorry, we did talk about lower bounds. But those are my options. Does that kind of make sense? Okay. So let's go through and figure out how we would maybe do this with our calculator. So I now know my only P over Q's I'm really interested are plus or minus 1, plus or minus a half, plus or minus negative 2. Those are my P over Q's. I'm trying to erase some stuff here to give myself a little bit more room. What you're going to do on your calculator, once you've typed it into Y1, maybe you've adjusted your window a little bit to be confident in your zeros. We're going to actually ask the calculator to find a 0 for us. Okay? So I'm going to go right there and find that 0. So this is the way we do it. Go second, and then calc. And we're going to get down to the 0, option 2. All right. Now I'm going to find this first one over here on the left. And all it means when it says left bound is that it wants your cursor to be to the left in regards to the x value, to the left of that 0, right? Okay. Now I don't know how this is, because this is a really steep line or curve. Okay, it does show up a couple times. Last class we did one where you know, I don't see my cursor, but I do know that it's below the x-axis, right? By looking at that y value. And then once I pushed the right button, it jumped it up to somewhere like that where I couldn't see it, right? So both times I'm choosing a left bound, and I should have hit enter. So we can back and do this. So I hit enter on my left bound. I couldn't see my cursor. I go, I hit my right button one time, and I still can't see my cursor, right? But I jumped from a negative y value to a positive y value, and then we have a theorem last week that said when that happens, what has to be in the middle? A 0. You had to cross the x-axis at some point. Okay, that's the intermediate value theorem. So even if you can't see your cursor, the information that's provided down here is useful to you. Okay, so I'm going to hit enter, and what my calculator is going to do is going to go through and find the ordered pair that has a y value of 0 there in that kind of restricted domain, and it gives me -2. So that tells me that -2 would have provided me in this synthetic division, -2 would have provided me a 0. Okay? Now, here is where your calculator does not always provide you everything you need to know. Because it's a 5th-degree polynomial, we see that we have 3 zeros up there, right? Chances are it probably means that one of those might be of a multiplicity, right? Does that make sense? Okay. So when you're doing these things, you don't necessarily know the multiplicity by just looking at the graph. Okay. So we have to be able to at least do the synthetic division and understand what that's telling us. So bring my 2 down. Oh. Do your multiplication correctly. Gives you -3, 6, 6, -12, -12, +24, -8, this was 16, sorry, and then +16, so when I add those together, I get 0, okay? Now here's another thing. This was a negative number, right? This is another situation where we kind of dealt with upper and lower bounds initially with this problem, but if I look at this quotient line, positive, negative, positive, negative, what happened? That's right. 2, -4, -3, 6, +24. I guess we're right then. But sometimes you're gonna get you'll get that positive, negative, positive, negative, positive, negative, positive, negative that you need, and realize that that is also a lower bound, right? Does that make sense? Okay. Obviously not happening here, but it doesn't tell me that -2 may, or it did tell me it's a 0, right? Okay. But it's not telling me whether it was maybe a double root or a triple root. So what we need to do is take 2 and try, sorry, -2 and try it again. Bring my 2 down, -4, -7, gives me 14, so there's 20, -40. My numbers are getting pretty large here to realize that, you know, if I keep going through with this, I'm not going to get a +8 here to give me a 0, right? So -2 is only going to have a multiplicity of 1, okay? So -2 multiplicity of 1 is a current 0 that we have. The next thing we have to do, okay, is to go back to this line. Go back to you always go back to your last quotient line. Don't ever, once you find a 0, never go back to the original polynomial. Does that make sense? Okay, because you're losing some work when you do that. Now I'm going to go use my calculator and we'll find another 0. Okay, so second calc, go to 0 again. I'm to the left of that 0, hit enter. Now I'm just going to make sure I'm to the right of that 0, hit enter, and I get -1/2, right? So I'll try -1/2. Bring my 2 down, gives me -1, -4, multiply gives me 2, there's my 8, -4, gives me -16, and now that gives me, what, +8? And there's my 0. Okay? So, positive, negative, okay, tells me for this, and it's not the original p of x, it's just this depreciated p of x, okay, which this is 2x to the 4th, basically tells me to the left of -1/2, you don't have any more zeros. That makes sense? Okay? Because of the alternating quotient line there. Which is nice because if this function, this p of x, is not going to have a 0 to the left of -1/2, then this one's not going to either. And that just validates it, confirms what we already knew. Okay. Now, remember, this is x to the fifth. This now became x to the fourth. This is now x cubed, right? Now, I don't know, because of the graph, I don't know whether negative 1/2 would have worked 2 times. Okay, so I'm going to bring my 2 down. Now I get negative 1, now I get negative 5. And now just kind of visualizing what's going to happen. We get negative 5/2, right? Add those together with 8. I'm probably not going to get positive 16 there, am I? Okay, so negative 1/2 probably just has a multiplicity of 1. So negative 1/2 multiplicity of 1. Okay. Maybe, now I'm just saying this because it is good to think about. If I would have found p of negative x, that's 2 negative x to the fifth plus negative x to the fourth minus 32 times negative x minus 16. So that'd be negative 2x to the fifth plus x to the fourth plus 32x minus 16. There's talking about p of opposite of x. This is Descartes' rule of signs. There's 1 sign change and there's 2 sign changes, right? So what that tells me, you either have 2 negative zeros or you have 0 negative zeros. There's our 2, right? Does that make sense? All right. P of x tells me that I have, what? 1 sign change. So 1 sign change, and P of x tells me that I have 1 possible positive real 0. So all these ideas, concepts that we've talked about kind of individually are visible as we go through these problems. Okay. Going through this, I'm not going to use a calculator, but I'm thinking that's probably a 2, right? Okay. So let's try this thing with 2. Bring my 2 down. 2 times 2 is 4. 0. 2 times 0 is 0. Gives me 8. So now positive 16 does give me 0, right? Okay. Now here's the thing. If that's 2, 0, 8, that is x squared, right? Okay. So now I have 2 as a 0, but I'm not sure about its multiplicity yet because this is the 5th degree. This is giving me 1 degree. This is giving me 2 degrees. This is probably giving me more than that, right? Okay, more than 1 multiplicity. So if I go down to this line, and that's really where you're always going to stop, is down to the quadratic line. You now have 2x squared plus 8 is equal to 0, right? Okay. Well, I'm going to go through, maybe you got options here. You could use factoring techniques, or you can use, I'm going to use square root method. I'm going to take a 2 out of everything, so divide all 3 parts by 2, right? So it gives me x squared plus 4 is equal to 0, right? Now here's the thing, does x squared ever equal negative 4? No, right? Okay. So really what happens then is that I get x to equal plus or minus 2i, correct? Okay. So this thing here really only has a multiplicity of 1. Okay. And what happens is that we end up with this 5th degree polynomial, but we get some imaginary results, imaginary solutions, okay, or imaginary factors, okay, complex factors, maybe a better word, okay. So what that tells us then is that this thing actually won't break down into all 5 linear factors being rational zeros, okay. What this thing breaks down to is, this is a 0, so x plus 2. This is a 0, so x plus 1/2. This is a 0, so x minus 2. Okay? And then, right now, we'll just write that it also has this factor, 2x squared plus 8. Okay? It basically tells us that that polynomial, though we can start breaking it down as far as we can, eventually becomes a product of 3 linear factors and 1 quadratic factor. Okay? After tomorrow, we'll be able to say that this polynomial is the product of three linear factors that come from real zeros and two linear factors that come from imaginary zeros. Okay, so tomorrow we'll start talking about imaginary values and how we can deal with factors using complex numbers. Okay. Put on your homework when you guys are going to be asked, can you look at a graph and determine the zeros? Okay, and then from that graph you determine the zeros. How does that determine your factors? All right. We're going to ask you to look at this polynomial and determine upper and lower bounds using some of those theorems that we talked about already. But the whole task of this process is to understand how factors impact your graph and how your graph impacts your factors. Does that make sense to everybody? Okay, going through these practices, synthetic division, long division, using these theorems kind of helps build that understanding. All right. Like I said, tomorrow we'll deal with what we call complex conjugates, okay, which really isn't all that hard. We've already done all the legwork. We just have to kind of realize how we deal with complex numbers, what we do with them. Then later in the week, hopefully we get to rational functions and graphing, like asymptotes and stuff like that. I'm kind of toying right now with the idea of, before we go to Thanksgiving break, to maybe have a test over stuff to make then